Haha! So, when I used to run groups, one of the biggest problems I had was that when new people came to the group, it was difficult for them to understand previous materials or previous information or previous discussions, simply because of the fact that there was a gigantic lead-in of information that was required, like in a cumulative fashion, to understanding the current concepts and topics being discussed. So in terms of this group, since I am leader, master, and controller in all aspects, unless you guys want ops or mod status, which I might give it to you, I've decided to put together a video series called Errata, like simple errata. It'll basically be, covering things that are very simple that should be discussed in whole before even coming to a lot of the presentations, simply based upon the fact that maybe the presentations are going to be complex. Now, as I give this presentation, I'm referring to the whiteboard. As you can tell, I love the whiteboard with all of my heart and soul. It is my true compatriot. It is my one friend. It is my love life. Sad. So anyway, I'm also going to be drinking a 40. Sad also. Less sad. But what we're going to be going over today, you guys have no idea how hot it is in here right now. It's like 96 degrees in the shade. Real hot in the shade. So, introduction to x86, 32-bit general architecture. But what we're going to go over in this stupid little video is the 32-bit Intel processors and how to kind of understand what's going on in terms of your computer and the processor and the instructions to which you're supplying to the processor via binary files. When you execute an executable, .exe on Windows, you're executing instructions. When you execute an L file in Linux, you're executing instructions. I mean, how those instructions get into the processor is a whole different topic, but at the end of the day, it's all just instructions. In the concept of, the exe and the L file, well, those are virtual. Those are executed in virtual memory and virtual processors, but let's just pretend that doesn't even exist. Let's just talk about the processor in itself. So, real simple. Here's the smallest computer I could basically visualize in terms of like a 1 foot or 1.5 foot by 8 inches square in this particular rectangle here. This is your processor. This is your Intel processor that you get from Intel or AMD, whichever you prefer. This is your memory. This is an input device. This is an output device. In order for all of these to communicate, you need 3 buses. You have the control bus, the address bus, and the data bus. The control bus is used to basically control things. The address bus is utilized to transfer address information upon request. So you want to get something out of memory, well, it has an address. The address bus is used to communicate those addresses so that the data bus can transfer data between the components. So you have input components, output components. Input would be like keyboard, mouse, whatever. It's more complex than that, of course, but in simplest terms, input, output. Output would be like your monitor, or say like a sound card, or something like that. System memory, of course, is your system memory. That's your DIMMs, your SO-DIMMs, your, sticks of RAM and whatnot. Your processor, of course, is this magical little box that exists on your motherboard for the sole purpose of processing instructions. What are instructions? Instructions are, as you would imagine, they are simple mechanisms that are pre-programmed in terms of the fabric of the logic fabric of the CPU to do things. They basically do math. They do math in all various forms. There's approximately 1,226 instructions in the Intel 32-bit CISC instruction set. That's complex instruction set. And it differs from different processors because complex instruction sets have wide features of different instructions that you can use that are, how you say, it's just more feature-rich. It's complex. It's more exhaustive. It's more available. So your processor has all these magic capacities, but they are separated in logical components. Specifically, there are 3 concepts, 2 units. The first unit is going to be the control unit. It's the most complex, where processors usually gain their advantage is not in terms of gigahertz rating or whatnot. I mean, of course, that does factor into it, but it factors more into how the processor is able to determine what you're going to do even before you do it. Like the control unit, basically, it gets instructions from memory, it decodes instructions, then stores data. That's the most simple control unit there is. Like in more advanced processors, there's like instruction pipelining. And there's different caches, level 1 and level 2, caches that basically allow for branch prediction, out of order execution, things that are just kind of tricky. Like sometimes, like if you see like somebody doing card tricks, like you can, if you study and maybe you record what they're doing, you can kind of figure out later on what they're doing. But there's a lot of trickery involved that makes it appear as if they're performing magic, when in reality, they're just performing a complex set of operations. The control unit does this. It performs a complex set of operations that basically are trickery, mathematical trickery, for optimization of processing effect. Okay, the more simple unit in terms of the processor itself is the execution unit, so control unit, execution unit. It does 3 things basically: simple, complex, and floating point math. There are instructions to do these things. It does these things, and that's all it does. It gets instructions, and it says, okay, well, I'm going to perform these instructions. That's it. Real easy. Of course, it's not that easy in reality, but conceptually, like when you're thinking about it as a human being, that's how you should understand it. You should get it in terms of the fact that this is an execution unit. It has pre-programmed settings in which it'll interpret data that you give it, much like an interpreter, like Perl or Python or PHP or Ruby. Like much like how they have like bytecode syntaxes and interpretive syntaxes, well, the processor also has interpretive syntaxes, and such as execution unit can take that input and it can output useful results. You transfer them across the address bus and the memory bus so that the application or the operating system can actually have useful data and use it and such. Okay, well, I said there were 3 units. The third unit isn't really a unit. It is a conceptual understanding. The conceptual understanding is that it is memory units. So in the case of the processor, we have what are known as registers. Registers are on-process, on-die memory locations, or many of them. In 64-bit, you have more and larger registers. In 32-bit, you have lesser and smaller registers. That's so stupid and cheesy. So cheesy. It's so hot, I have to have my 40 on a back of lights. Okay, so anyway. If you ever looked at any disassembled instructions, you'll see like move EAX to a specific location in memory, or move a specific value into a dereferenced register. Dereference means a pointer to the register. So, like if you ever look at that, you'll see these different mnemonics. Now, these aren't actually mnemonics; they're register mnemonics. They're very useful because what they allow you to do is manipulate data in a way that is entirely quick and without without actually leaving the processor really. You don't really have to actually go out across the address bus or the data bus and do anything when you're actually using registers, because it's all on die. It's right there. I mean, it's different when you're doing virtual processes and virtual memory. But for the sake of argument, understand that these should be on die, especially when you're in kernel. And if you're writing your operating system, on die. So anyway, you have EAX, EBX, ECX, EDX. EAX is an accumulator. This is where if you're running a function, if you're writing C, if you're returning a value, the accumulator is where it should be stored, EAX. Other than that, it is a general purpose register. EBX, ECX, EDX are all considered general purpose. ESI and EDI are specific for string operations. Like if you're going to be doing rep instructions where you're going to be doing transfers of data, like where you're going to have to be writing to a specific destination, Well, the indicator where you start reading and the destination where you where you write to, is going to be these two registers. They're going to be basically where you're utilizing them. ECX, which is the counter register in terms of those instructions, is used to indicate how many times you're going to be writing. So if you have a rep, like you're going to want to store the number of bytes to write in ECX, and you use ESI and EDI to specify where you're using, and then you use the move instruction or whatever. But usually it's move B, but that's too far ahead to actually do these writes. Now, the stack and the heap are two things I'm going to want to discuss later. But for the sake of this video, because YouTube is 10 minutes long at maximum, I'm going to say the ESP is the stack pointer and EBP is the base pointer. The base pointer a lot of times is reused as a general purpose register. In some archaic implementations, some older versions of Windows, the base pointer is utilized for pointing at the base of the stack of the application or the context you're running in. But ESP will always point to the current location on the stack that you're running in. Now, you want to research stack later so that you kind of understand that. I might make another Errata video about the stack itself, all by itself, but again, time constraints. So the next registry you have is instruction pointer, EIP, extended instruction pointer. It points at the instruction to execute. Remember I said the execution unit is responsible for executing things? Well, it knows where to execute next because the execution pointer points at it. Memory exists. It is a real thing, and in that real thing there are real entries, and those real entries contain real data. If the instruction pointer points to that data, it'll read, translate, transcribe, and execute the data required at that location. When you're actually taking advantage of an application and trying to control an application, controlling EIP reliably is really what you're going at. When people are writing exploits, they're looking to control EIP in a meaningful way. So next kind of registers you got is controlled register. CRO is system flags. CR1 unused, CR2 page fault data, CR3 page directory info, and CR4 is processor features. You might want to investigate these yourself. It is so hot in here, you have no idea. System flags is the most important, otherwise known as E-flags. Flags are just single bit flips, so it's 0 or 1, 0 or 1, or 1. So let's say we have a 32-bit value. Well, that's 32 flags that we can implement in either 1 or 0 configuration. So 3 different types of flags in terms of info. We're almost done. Stay with me. 3 different types of flags. You have status flags, control flags, and system flags. System flags are relevant. Control flags almost irrelevant except for how they're implemented. Only 1 control flag. And status flags are, these are interesting for researching exploits and stuff, because you have the carry flag, you have the overflow flag, you have the sign flag, the 0 flag. Okay, carry flag indicates whether or not an operation has mathematically required a carry, meaning that it requires a carry from a value higher than it in order to actually complete the operation. Now, the reason that this is important for us as exploiters or researchers, where the hell we are, is that the carry flag can a lot of times indicate whether or not an integer overflow has happened. So if you have a debugger and you're single-stepping the application, and you're going through the application, and the application doesn't take very long to run, well, you can analyze the carry flag on each iteration and determine whether or not an integer overflow occurs. Integer overflows, of course, meaning, okay, let's say we have 00 to FF. Okay, we have 1 byte to store information. We can go from 00 to FF. Well, when we hit FF, which is 255, or 256 technically if you count 0, well, what happens is it doesn't go FFF0, it goes 00. Instead of going to 3 digits, because it only has 2 digits of space, it goes back to the lowest 2 digits available, which is 00. Okay, so if we indicate that we have a carry flag, well, sometimes it means that we can control or undersize things. We can oversize things. Sometimes we have the ability to make things bigger or smaller, wherein they're going to be written to potentially with an oversized value. So if we make it smaller and it's oversized, well, potentially we can overflow past it in memory and actually control memory that way. Parity flag, not very useful to us. Adjust flag, not very useful to us. The 0 flag, if an execution, if an instruction is executed and the result is 0, the 0 flag is automatically set. The sign flag, it's set automatically after every single instruction, and the sign flag represents whether or not the most significant bit in the application is 1 or 0. It's for signed operations on signed integers, meaning you can determine whether or not a value is positive or negative. That's something you're going to want to research more, investigate the term 2's complement. There's a good Wikipedia article on it. You can read up on it and get familiar. The overflow flag breaks under the carry flag. It indicates whether or not something is overflowed. I find the carry flag more reliable. Control flags, direction flag. Okay, Intel 32-bit. I have to talk really fast because we're running out of time. Direction flag indicates whether or not we're going little Indian or big Indian. Google the terms little ENDIAN and big ENDIAN. It basically determines whether or not things are written in network byte order or whether they're written in, I guess little Indian is the only term for it. System flag, very important. Trap flag indicates whether or not we're in single step mode. We have the interrupt flag and the IO request privileges flag and the nested test flag. And then we have the resume flag, which is important for debugging. It indicates whether or not we're going to resume back into single step or we're going to resume back into normal execution. Virtual XO 8086 mode indicates the size of the registers that we're going to be using. This can be set with prefixes 0x66, I believe. That is something we're going to cover later in terms of instruction compounding. We have alignment flag, a virtual interrupt flag, a virtual interrupt pending flag, and identity flag. I'm not very familiar with all of these. Like, I should probably be more familiar with them, but I had no reason to use them in the past. That said, I think that's a good start as far as this errata goes. Like, in the next section, I might go over Intel bytecode syntax, or I might go over the flags in detail some more, or how to leak information. Like, sometimes you can get like useful information from the control registers. Like, I believe it was CR3 that was useful for getting kernel information leaks in Linux. Like, you could find out whether or not you were in a virtual machine or not in a virtual machine. I think it was CR3. But yeah, hope you enjoyed it.